So this next section is about running a two proportion z-test. And the two proportion z-test, as you might be able to guess, has to do with proportions, and it also has to do with two independent samples. So the hypotheses will be of one of two forms. You have the choice to either write your null hypothesis as P1 equals P2, or you can write it as P1 minus P2 equals 0. Notice how all I have to do is a little bit of algebra just to get from the first to the second. Either of those is okay. Do whatever works better for you and what makes more sense for you. The alternative is pretty much always going to be P1 is either greater than, less than, or not equal to P2. And then the other way that you could write it is like this. And there have been rare occasions when there have been problems where it's been subtraction, it's been something other than 0, but that's so rare that happens that we won't really focus too much on that, but one of those might come up at some point or another, but it's unlikely. Okay, so our conditions are going to be the same as what we did for a z-test, except that we need to check them for both samples. So my first condition is going to be that it's a random sample. And actually, I should say random independent samples. So what I mean by independent is that the two samples are completely separate. Like, you don't have any one person who's affecting another person. We'll talk a little bit more about this in class. The basic idea is that the samples are independent. They have nothing to do with each other mostly. They don't have any of the same people. They're just going to be completely different samples. So the next thing that we need to do is we need to do our success-failure condition. So before, if you remember, it was the NP is greater than or equal to 10. In this case, we actually have to do it with P1 and P2. The only thing about this test that's different from the previous z-test is that you might notice if we look at our hypotheses, we don't actually have a number for our P1 and P2. So actually we're going to use our P hats here. So that's just an important distinction to keep in mind. And then we do the same thing with our 1 minus P hat, or if you want, you can call it the Q hat. So we need to check that all of these are greater than or equal to 10. And then the last one is the 10% condition, which once again, you have to check separately for both samples. Okay, this is the second example of this section, but our first example for a two proportion z-test. They want to know if teenagers are losing their hearing. So what we have here is we had a study of 3,000 teenagers in 1998 to 94, and we had another 1,800 in 2005 and 2006. So just note that these are two separate samples. We're going to assume that nobody was included in both samples because they're at least more than 10 years apart. So what I tend to do if I get a problem like this is I tend to start off by writing down all the information I know. So I'm going to start with my 1998 to 1994, or 1988 to 1994. And I know a few things there. I know that my sample size, which I'm going to call N1, was 3,000. I know that my P hat, my sample proportion, which I'm going to call P1 hat, was 0.15. I'm going to call my 1 minus P1 hat Q1 hat, and that's going to be 0.85. And then I'm going to do the same thing for the other sample. So it's a good idea just to keep things organized, because there are a lot of numbers in this problem. And then I'm going to call the 2005 to 2006 the N2 and the P hat 2, and so on. So what we're going to do now, this does end up being a long process, and I'll be completely honest with you, you're most likely going to be doing this type of thing using your calculator. It has some great functions that will allow you to do all of this. But I think it's also important that you know how it's done, so I will show you what we're actually going to be doing here. Okay, so we're going to start by writing our hypotheses, but before I write my hypotheses, I'm going to define parameters. So P1, notice how there's no hat, P1 is the proportion with hearing loss. You can say of teenagers with hearing loss in 1998 to 1994. And then P2 is going to be the same thing, but from the other sample, from the other years. Okay, so we have our parameters defined. Now we are going to do our hypotheses. And I'm going to write the null hypothesis. So our null hypothesis is that the two proportions are equal, which I will write as P1 is equal to P2. The alternative hypothesis is going to be that the proportion of hearing loss from 2005 to 2006 was greater than the proportion of hearing loss from 1998 to 1994. By the way, you might notice that I put my P2 first instead of my P1. It's completely acceptable to do P1 is less than P2. However, the reason I'm doing it this way is because once I work this problem out, because I have my higher number first, once I work the problem out, my numbers will be positive, which is really nice. So, and actually, just to be consistent, I'm going to write this as 2 and this is 1. And so now what we're going to do is we're going to actually rewrite these as H0 is P2 minus P1 equals 0. And HA is P2 minus P1 is greater than 0. So we'll do it that way, and then having it written that way is going to help us in a future part of this problem. Okay, so our next step is to check conditions, and you'll notice I wrote them out, and they are a little bit long, which is why I wrote them out beforehand. You can see that the samples were randomly selected and independent of each other. With the NP and 1 minus P, the one thing I want to caution you about is here. Usually we use the P that we had in the hypothesis. However, if you look back at the hypothesis, you don't actually have a P. So what we're going to do is we are just going to use the values that we were given for our P hats. That's really the only thing that we can do for these. So that's going to be how we check these conditions. The third condition, the 10% condition, you'll notice I did it kind of like the backwards way where I multiplied the sample size by 10. Either way is okay. You do have to check it for both samples. So that's the important thing for all of these is that you check them for both samples. So all of these are satisfied. So we are going to use a 2 proportion Z test. Okay, so here is going to be the tricky part here. And so before we go on to the mechanics part of our test, we actually need to talk about one thing. And so the important thing that and by the way, you are going to be shown how to do this on the calculator. So if this is really hard for you, I'll show you how to do it on the calculator, but I want you to really try to understand how to do it by hand. So now, if you remember when we were, in the last chapter, we were learning about hypothesis tests. So when we run a test, we are assuming that the null hypothesis is true. Here's where there's a little bit of a weird thing going on. So our null hypothesis, remember, is that our p's are equal. However, you will see clearly that our p hats are not equal. So because we make this assumption, we need to do what's called pooling or combining our sample proportions. So we must pool, and you can just say combine the sample proportions. So we know from the intro to this example that our P1 hat was 15%. Our sample size for that one was 3,000. So actually what happens is I'm going to call this next variable, I'm going to call it x1. And that's actually how it's going to be listed on your calculator. So this is going to be the number who experienced hearing loss. So, and then this was in the earlier one, 1998 to 1994. And we're going to have the same thing for the other year, the other span of years, and we're going to call that x2. So the x1, we had 15% of our sample of 3,000. So this x1 is going to be 450. And then our x2 is 19.5% times that 1,800. And that is going to give us 351. Okay, so now what I'm going to do is I am going to combine these into one sample proportion. And I'm going to call it P hat C. C is for combined. And the way that I'm going to work it out is and this P hat, remember, is assuming that this is going to give us the P hat that we would get if we assume that our null was true. So what we would do is we would add together the sample sizes, and we are going to add together the number from each one. And this is going to be our overall proportion that we have. So we end up getting 801 out of 4,800, which gives us 0.167. This is our combined P hat. So this is looking at the entire population of the 2 years, or the entire samples from the 2 years. Okay, so now we have our, we have a few things. We have our P hat of C. We know that it's 0.167. So the next thing I'm going to give you is the pooled standard deviation. And so the pooled standard deviation is going to be the same idea. Here's the difference. So we're going to do the P hat C times the 1 minus the P hat C. And then we'll do that over N1 plus P hat C times 1 minus P hat C. And we're going to do that same thing over N2. So you're going to see this formula written in several different ways. You might see it written as the P hat times 1 minus P hat. Then that all times this. You might see it either of these two ways. That's fine. Just know that they're the same thing. So I'm going to use the first one. However, I found that is a little bit easier to understand for people. So what we're going to do is we are going to find the whole thing there. It's going to be 0.167 times 1 minus 0.167. And that's going to be over my first sample size, which is 3,000, plus the same numerator times 1,800. And you're going to find that your standard deviation in this case is 0.011. Okay, so let's put this all together now. So you'll see on the left I rewrote the hypotheses that we have. I also rewrote our standard deviation, our P1 hat, and our P2 hat. Actually, we don't need the combined P hat anymore. We only needed that to find the standard deviation. The other thing is, if we look back at our hypotheses, what we're going to do is we are going to assume the mean is 0. That's what we're going to do there. And we want to figure out the probability of getting our sample, the difference in the sample proportion or more extreme. So what we're going to do right here is I am going to put right here the P2 hat minus the P1 hat. So I'm going to put the difference between those two proportions. And then that's going to be the P hat that I put here. So I think this gets confusing for some people because there are a lot of P hats happening here. So this will be 0.045. And because my alternative is greater than, I'm looking for everything greater than that. So then to do my p-value, I'm going to do normal CDF, and then 0.045, you can do any big number. My mean here is 0. My standard deviation is 0.011. And when I did it, I ended up getting about 2.15 times 10 to the negative 5. Actually, I've done it, I did it two different ways, and because of rounding, one of them I got 2.58 times 10 to the negative 5. That's fine. 10 to the negative 5 is such a small number that if you're a little bit off on these, it's not a big deal. So this is a very low p-value. So we will write our conclusion, and then we're going to be done. So hopefully the conclusion for this will seem very familiar. So we're going to say, because the p-value is small, I reject the null hypothesis. And it's actually very small. So we're going to say there is strong evidence that the proportion of teens with hearing loss has increased. So, the AP test loves asking questions like this. They say, Apple introduced the iPad between the two studies. If the results are statistically significant, which they are, by the way, because we rejected the null hypothesis, can we blame iPads for the increased hearing loss? And the answer for that, I'm hoping you realize, is no. Because we didn't do a controlled experiment, we can't do that. So we can't conclude any sort of causal relationships without doing a controlled experiment. So this is a nice little review from chapter 4, but hopefully you remember that.